Hi, welcome back to Statics 1. So today we're going to start doing solutions of actual real live structures. And this is kind of a cool thing, and I remember when I was in school and first started actually analyzing structures, and hopefully you're going to find this to be interesting. It is kind of a narrow set of type of structures and assumptions that we're going to make about these structures that later on, when you get into Statics 2, and when you begin to take structure, like concrete design and steel design, you're going to relax a lot of those assumptions and be able to analyze much more complicated systems. But for now, we're going to start with basically what we call trusses. So this is structural analysis. So what does that mean, structural analysis? It means we're going to look at structures and determine what are the internal forces within them. And for the most part, so far we've only been looking at external reaction, external support reaction, external loads. Now we're going to begin, at least in a very limited way, or very narrow sort of way, looking at the internal reactions. And we're only going to look at pure compression, pure tension, which you'll see later when you take Statics 2 that's only part of the story. It's actually much more interesting than that. Structural analysis. We are going to be looking at trusses. And a truss, as defined in our great textbook, is a structure consisting of slender members, as they call it. In other words, long relative to their cross-sectional area, and they are joined at their endpoints. The structure consisting of slender members joined at their endpoints. Alright, so what the heck does that mean? Let's look at kind of a picture of what we call a roof truss. I'm going to try to draw this in 3D, if I can. This is actually in the textbook, so if you don't like my drawing, you can go look at the one in the textbook. I'm going to do this so I can copy it. So this is a roof truss. The roof truss, not surprisingly, holds up a roof. It's a truss that holds up a roof, supports a roof. And so, and it might look kind of like that, like that, like that. And and there are different ways in which these are joined. There are different patterns of trusses. This is sort of a conventional roof truss, but you can do it many different ways. So this is the end, kind of in the end, and then this would be attached. I'll just sort of conceptually put a hinge over here and a column. Probably wouldn't be exactly, and I'll put a roller over here just so we know we can solve another column. And I'm going to do my little 3D to see how good this is. So here's the rest of my roof. At least a good part of it. And I'm going to put this back here like this. Okay, hopefully that makes sense. Roof. So here's the roof itself. And back here, this would be supported as well by another column in the corner. And then we have what we call purlins. And this is a term I'm not really familiar with, but it kind of looks like that. This is a purlin. And I suppose there'd be one here as well at the peak. And on top of this would be the roof itself, the shingles and the tar paper, maybe probably plywood. And so there is kind of there's a concept called a load path. And it basically talks about how loads get shifted from one structural component to another. So we have our roof, load going to the purlins, which would shift the load, so the load would be on these like long members, and that would shift the load to the trusses, which have to support the purlins, and then the trusses basically transfer that to the columns. Okay, same thing with the bridge. And you'll see frequently trusses like railroad trusses, railroad bridges that are constructed from trusses, or constructed as trusses. So let me draw one, and let's see how good I can do on this. This one's a little bit, that's pretty horrible. But let's see if I can do better with our railroad truss, or truss bridge. If I could talk, then I'd probably. Alright, that's not too bad so far. This is the side where the truss is, and here's the other side, and then here's where the train tracks or roadway would go. Let's draw this like that. I don't know. What do you think? Alright, well, that's pretty good. And now I'm going to make a truss in here, and I'll do, there's a bunch of different styles of these trusses. I'll try to do it. I'll do one more like that. Okay, so that's the truss. So this is the truss itself is on the side. And again, we have a load path. So you'll have, in this case, you'll have the deck of the roadway, or the slab. And I'm going to put that, I don't know if we can see, I don't know how we're going to draw this. I'll try drawing it, but, okay, so you have, that's the deck. Okay, the concrete, and if it's, whatever else is in the roadway. And it could be the cars themselves, right, or the tracks. And then we'll have what are called stringers, and those are going in this direction. Oh, now this is going to be a mess. Let me do this in green. So imagine these stringers are attached on the roadway. Basically, they're holding up the slab. And then we have also floor beams that are going from one side to the other. So we might have one floor beam. I'll do it in blue. Maybe this will work. So we might have a floor beam. Everywhere you have one of these connections in the truss, you might have a floor beam. So here's a floor beam. Well, this is pretty awful, but I think hopefully you get the idea. So we have the same thing, just like we had a load path here, which went from the roof to the purlins, the truss to the columns. In this case, our load path is going to go from the load path. We'll go from the deck to our, what they call stringers. Oh, excuse me, deck. Yeah, I think the stringers go on top and then the floor beams are underneath. Stringers to the beam, what do I call them? Floor beams. To our truss. Obviously the truss is going to support those floor beams, and that goes basically onto the columns, which are supporting on the ends, or the corners. So that's kind of what we're going to be dealing with, trusses. Now there are some simplifying assumptions that we're going to make in analyzing these trusses. And what we're going to do is we're going to analyze these trusses so that we can tell, based on a given loading, what are they going to be, the compression or tensile force in every one of these members. But we have to make certain assumptions because we are in statics 1, and later on when we get into statics 2, we can relax some of those assumptions and solve more complex problems. Okay, so what assumptions do we have to make in order to solve these trusses based on what we learned in statics? And it's really all based on Newton's laws of motion. So assumptions we're going to make, I'll draw a line here. Assumptions to analyze they're like a little bit limiting, but in some ways, based on our description of load path, they're not too bad. But the first of which is that the loads are at the joints. So if we were to describe the loading on the truss here, we would only put them, and this is kind of a complex picture here, but we put a load here, we might put a load here, we might put a load here, we might put a load here, but we wouldn't put a load in between the joints. That, if we did that, you couldn't really solve this. So in essence, we're going to be neglecting the weight of the member itself. Although you can handle that by assigning the weights at the endpoints. So I'll add that on, and this is almost like 1A, but 2, which is neglect weight of the structure, which seems a bit odd, but we can deal with it. And as I said, we can assign the weight of like this member by assigning half of it at one end, half at the other end. Now the nice thing about having the loads all at the joints is that all of our members are two force members, meaning that the forces are all aligned with the axis of the members. So it's very important. That actually enables us to solve this. There's one more thing we need to say, which is that the joints are smooth pins. So they're not actually, the joints are smooth pins, they're not actually providing any resistance to rotation at any of these joints. And when I say joints, that would be wherever the members come together. Those are called joints. All right, and typically, it's not, I mean, if you ever look, next time you're out, look at like a metal bridge, where there's a truss, and you'll see something called a gusset plate, typically. And so you'll have members coming in like this, and it doesn't look exactly like that, but we'll put in a plate on here, and then we'll screw it in. You'll see there'll be like a lot of screws. So essentially, it's not a smooth pin, obviously. We typically use gusset plates. But as a first order approximation, this isn't too bad, because if they are in fact two force members, you wouldn't expect that there would be moments occurring at the joints themselves. So those are the assumptions we're going to make. And so the next lecture we're going to talk about what's called the method of joints, which describes how we can actually solve for either the compressive or tensile forces within our members, as opposed to what we were doing before, where we're just getting like the response, kind of boring, just getting the response reactions. Now we're actually going to get into our structure, and really the goal here, it's not like these are techniques you may use in the future, but the goal is to help you develop both engineering judgment and some intuition about how structures work. So that's it. So next up is method of joints. Email me if you have any questions, and I'll see you in class.